So today the focus is, as promised, is that we're going to be talking about a different type of interaction. So as a reminder, that first course was the course where we talked about non-interacting systems, so we all were oriented about how those worked if they were active instead of being passive. And now we're trying to understand what happens when there's interactions. And the last time we talked about a field of spins that aligned. And today the focus is going to be on a second type of interaction, which I'm going to call steric metric interactions. And so, if you want, there's the QR code for the lecture notes. The third set of lecture notes is up there, and you can see it. Although, of course, you all know, right, that if you actually write your own notes, studies, like very good peer-reviewed studies have shown that you learn more, right, if you write your own notes. I mean, I don't always take my own notes either, but just, in the ideal world, that's what we would all do to learn things. Okay, so interactions 2. It's all very official. This is the second one, is steric metric interactions. And what happens when you have active particles with those? And so first, I want to say that we're going to focus first, and actually, to be perfectly honest, kind of only, because I'm going to run out of time, on particles with spherical symmetry. And this really, really means that there's no alignment due to steric effects. As I'm sure many of you know, if you put objects which look like an ellipsoid all together, even if they're passive, they will start to align in order due to sort of free volume entropic effects, right, for example. But we're not going to focus on that situation right now. Okay, so for this sort of system, people write down a lot of different types of interactions. So let's talk about a couple of them that you might see if you're looking at this literature. So you start by saying, okay, there's a potential between particles I and particles J. And so let's draw a picture of what we mean. So this is one spherical particle I, one spherical particle J. This one is a distance Ri from some origin. This one is a distance Rj from some origin. And then I can describe the distance between these two objects as a vector, Rij, and I can put a sign to it if I want. But usually I'll just take the absolute value. So, and in this case, we're going to be considering two-body potentials, which do have the functional form of they're dependent on the absolute value of the distance between Ri and Rj. And so this, when I use this notation, I mean V of this Rij vector, okay? And so I'll give some examples of these interaction potentials. One example is a Leonard-Jones potential. And so that is Vrij is some energy scale times sigma, I'll say what that is in a minute, over Rij quantity, this whole quantity, usually people do it to the 12th, minus sigma over Rij quantity to the 6th. So for example, and the sigma is just some estimate of the radius of these particles. So people sort of fudge around with what this exponent is, but this is always a 6. Can anybody tell me why it's always a 6? Does anybody know? It's kind of cool, right? Somebody know? What? Exactly, it's a van der Waals interaction. So you can show, by sort of fairly straightforward means that if you have sort of dipole-dipole interactions like van der Waals, that'll generically give rise to sort of an attractive interaction that scales to the 6th power.
3D, right?
3D, yeah. And then the other thing to say is that you know why people pick 12? Because on early computers it was a lot faster to have it be double of the 6th, right? Okay, so that's kind of cool, okay? Not double, square of the 6. Okay, so that's Leonard-Jones. And so, I've had a few people talk to me when you're sort of talking about modeling, for example, cells or something. Can you do something like a molecular dynamic simulation to model interactions between cells? And the answer, you can, and people have, using like this, which is sort of a standard coarse-grained molecular dynamics interaction potential, right? So a lot of what I'm going to say today, it doesn't depend on the details of the potential, but this is one you can use if you have in mind something which has an attractive piece and a steric repulsion piece. Okay, but we're going to mostly focus today because it's a little bit simpler on things that don't have an attraction. Okay, and so then the potential is, I'm going to write it in this way, which is V of Rij is some energy scale times delta Ij to some power. Okay, and now I have in mind that if I have two spheres and they have an overlap delta Ij, this potential just says that they pay a penalty if that overlap is positive, and this is the potential if Dij is greater than 0, if the overlap is greater than 0, and it's 0 otherwise. So they don't interact at all unless they touch, and then once they touch, they pay a penalty that's proportional to how much they're overlapping. There's lots of choices you can make for alpha, but the reason that you can do this is because if you thought that these things were somehow behaving like idealized springs, that would be a harmonic interaction. So alpha equals 2 would be sort of a harmonic interaction. And then you can actually calculate, and I don't know how many people have done this because physicists don't usually take solid mechanics, but you can show that alpha for elastic spheres, this interaction actually to sort of lowest order in the overlap goes like alpha to the 5/2, and that's called a Hertzian interaction. So this is another model that people use to model particles that are squishy and soft and don't have an attractive interaction, just to give you some flavor of the type of things. Okay, so this is interaction that we're going to start to think about. And then I'm just going to sort of review, because reviewing is good, that if I was to add activity or self-propulsion to a particle like this, what I'd want to write down just as a recollection from a previous lecture is I'd want to write MA equals F, right? And so I'll just write it out. This is F interaction plus F self-propelled plus F drag plus maybe even some thermal fluctuations, forces due to noise. Sorry, these boards just don't erase very well. I think it might be partially the eraser's fault. Okay, and so the thing that we can do here is let's pretend that thermal fluctuations aren't important. We'll take the overdamped limit again. So we talked about that a bit. Limit. It's the same limit. So this is when you are neglecting inertial effects. So it's the same limit as when you take the Reynolds number to 0 and the stuff that people have talked about earlier. That's a connection. Okay. And then, so I want to write this then is the sum over sort of neighbors, or actually I can write it over all particles if I want, because I'm going to write it as the derivative with respect to this V of Rij with respect to Ri. So this is just writing the force, the interaction force. And then this will be some self-propelled force in some direction, and then we'll have a drag term like we discussed earlier. Okay, and so then the equation of motion for stuff in this type of system is just very simply related to what we saw before, which is dri dt is equal to F naught over the psi n hat minus 1 over drag times the sum, and I'm going to write it now in it's a gradient. Okay, and if I introduce, because people do this in the literature, so I'm going to do it here too, so when you see it, you're not weirded out. People just replace this thing by a mobility mu, okay? So Why, I don't know, because it's just the same number of parameters. Okay, but it's what people do. Okay, and then so I'll just write this you can write it in a very succinct form. Ri dot is V naught n hat minus mu times sum over j grad I of V Rij. Okay, and this is pretty straightforward, but again, just so we're all on the same page as we move forward. Okay, so the first thing I just want to give you a little bit of a flavor of when we go to high densities now, what can happen in these types of models. And there's two things that I'm going to talk about today. So there's sort of two kinds of things that can happen. One of the things that can happen is what's called a motility-induced phase separation, which I've alluded to. Okay, and just to give you a little flavor of what that looks like, and actually I'm going to give you a reference right now because I won't be able to cover nearly everything there is to cover about this topic. So there's a nice review by Cates and Taylor, and it's in Annual Reviews of Condensed Matter Physics, and that's in 2015. That really goes into this in a lot more detail, and it's pretty readable, I would say. So I would recommend that as a review. Okay, and so what's the important thing that I want to, just to give you a flavor of where we're going, we want to explain the following observation, which is that if you simulate this thing with, I don't know, this potential for a bunch of particles, okay, what you find is something kind of cool. So I'll write it as sort of they do in this review, but we'll write it in a few different ways as we go. But there's something on this axis which is the self-propelled velocity. You can think of it that way. And on this axis will be the density of particles in your system. And what you find, which is really neat, is that there's sort of a phase sort of transition, or sort of what looks like, if this was an equilibrium system, the following setup. Where in this regime, you seem to get phase separation that looks spinodal. And so this is what's called a spinodal line. Okay, and so what I mean when it looks spinodal, I mean that you basically find that there's a characteristic length scale at which there are two phases, a high density phase of particles that are all stuck tightly together that look kind of like a fluid in some cases, or a glass in some cases, or a solid crystal in some cases, and then a low density phase that looks like a gas. Okay, so it's like a phase separation here. Then you get some region of space where it looks like you also get phase separation, but it happens by nucleation, right? So you have to sort of have a fluctuation, it seems, that's required. And so then this would be what would be a binodal line. And then in this regime here, things are homogeneous. So you don't get any phase separation into dense and not dense phases at all. Yes? So can you speak up? They have the same speed all the time. That is correct. So they have a self-propelled, so what you just told me, which is exactly right, is that if I want to know what the actual velocity here is, which is this side of the equation, it's the velocity it wants to be plus some changes due to interactions with other particles. So you're precisely right, but there's a force that these particles generate on their substrate, but that they might not move at that speed anymore because they're interacting with other particles. Great. Any other questions? Cool. Okay, so that's one thing, and we're going to talk about that first. But before we get there, I also want to say where we're going so that everyone is really excited. Okay, so the second thing we're going to talk about is Glassy and jamming. Glassy dynamics and jamming. Okay, and that's because when you get to really high densities in these systems, you get a different type of transition from the one I just hid from you. And it looks something like this. So I'm going to put this on a log scale, but log of the self-propulsion parameter, and then some density, but I'm going to sort of talk about in a second what that axis is. And what you see is there's some regime that looks something like this, and you get an unjammed system here and a jammed system here. So this is a different type of transition. Okay, and so the control parameters are, of course, like sort of V0, which sets something like injected energy scale, right? And then, which is just the self-propulsion speed, which we already talked about. And now I've introduced a new variable, phi, which is called the packing fraction, because now my objects have a radius that they like to have. So once that happens, then I can write this quantity, which is sort of the size of all of the particles divided by sort of the size of the box. So this is the, you know, I'm doing it for 2D disks here, but you could do it obviously in any dimension. So this is the area of a box, and this is the area of the disks. Okay, and so the idea here is that you want to know how much of the space in my box is taken up by disks, and that's what this packing fraction tells you.
And C is related to rho?
Right, yes. So rho is just the number density, and so it's the number density per, you know, volume. And
So how does this go? Because it's the same, essentially the same for the parameters, right?
yes,
Other-
yes.
so with the other one?
Right. Yeah. So there's a regime. So there's a critical. Sorry to interrupt. Yeah, there's a critical sort of row at which, depending on the other parameters of the problem, you stop getting sort of phase separate. And actually, maybe if I can hold your question, I will come back to it. I hope in like 2 minutes or 3 minutes. Okay, because I want to talk about the intuition of this, and that will lead to a picture of why that other thing happens. Okay, cool. Is there a question? Yeah. Is the jamming thing related to percolation at all? That is a very deep question. So it's not related to site percolation or any of the standard percolations. It is related to what's called rigidity percolation, but that is a very different animal than standard percolation theories. And so there's a lot of beautiful work to try to sort of use percolation theory, but percolation of rigidity to try to explain the jamming transition. And I would say it's still a work in progress. Okay, I'm happy to talk to you about it more later. Okay, any other good questions? Okay, so this is what we have going on for the next, hour and change for all of you. Okay, so motility-induced phase separation. Let's talk about that first. So we're going back to MIPS. Okay, so for motility-induced phase separation, let's just talk for a minute about the intuitive mechanism. Like, how is it possible? Okay, so in fluids, if I get phase separation, it's because I have attractive interaction between the molecules, right? And then it's very sort of straightforward to figure out that that has to be the case, that I can get phase separation. Okay, but here these are purely repulsive particles. So why are they doing something that looks actually very nearly identical to what attractive particles would do? Okay, so let's to think about that. I want you to draw, or in your brain draw if you're anti-note taking, a picture of two particles that do this. Okay, and then I want you to talk to your neighbor. So talk to somebody in your vicinity for just a minute about what you think would happen, how a situation like this might be related to motility-induced phase separation. Why would a geometry like this be of interest for us to talk about? So this is a particle, self-propelled particle that happens to be oriented this way. This is a self-propelled particle that happens to be oriented that way. Think, okay, and talk. You're not talking. I borrow your desk for a second?
I think over here because there are active particles that is so for those two particles, that is a fine. There is no temperature.
So that's a good question. It's a good question. So what is the equation of motion for those two particles if they start out that way? I told you what the equation of motion was, right? Okay, so is anybody brave enough to volunteer some thoughts that they had during that discussion that they think might be relevant for future discussion? Yeah?
Well, unless they're going to equally distribute space,
Right, so the first thing is you notice that this is sort of like a microscopic cluster, right? What makes it, okay, so what makes it a cluster? Because like I could have this happen just like one time and then at the next step I could have something totally different, right? So what makes this a long-lived cluster? Is there noise? Sorry, and I should have been more clear about this. I have intended that these are self-propelled particles, so they all obey this rule, right? So they are this thing, and oh, yes, this is a self-propelled particle, so it has the same noise that we wrote a long time ago, which is that theta dot is equal to some white noise, right? Yeah.
That's sort of a zero set. They have to exactly align.
Mm-hmm.
But if you get a cluster of 3 particles, there's a significant fraction of states where I can assign the velocity such that they all sort of continuously bump into each other, and then that cluster stabilizes itself.
Great. So what you've just suggested is the fact that there is a sort of caging effect, that once I have particles that are sort of together, that they kind of stay together because they're colliding. And that's really important, okay? But can I ask it slightly different? So that is definitely a right answer, but there's more than one right answer to this problem, right? Does anybody have any other ideas about this particular setup and why it might be useful to think about? Yes? There is a persistence in the motion, so why is that important? That's it. So that was beautiful. I don't even have to repeat it. Did everyone hear that? Okay, so basically the idea is that these particles are persistent, right? They have a persistence time, which we talked about, some time ago, right? And so what that means is if they stay like this, if they were, so this is their motion at time t equals 0, right? Pushing into each other, right? If they were Brownian particles, at the next time step, they would be moving any which way, right? And so they wouldn't stay together for any length of time. But because they're persistent particles, right, there's some time scale for the rotation of them away from that state. And so that's going to generate an effective long-term, long-time interaction between them that looks a lot like an attractive interaction, if you think about it, right? In terms, if you just looked at the dynamics. Is that cool? So those two effects that were identified by probably many of you, and then also by your fellow students, is exactly what we're going to be talking about. But that's the intuitive idea. So let me write this down very briefly. So these particles stick together. So they don't stick together other than I happen to have a fluctuation where there's an ensemble of states. There's some particles that are oriented not in this way. I'm saying consider a set of particles that is oriented this way. That's the idea. Okay. These particles, if they get into this configuration, then once they get there, they're stuck for a while. And they're stuck for a persistence time, for a time that's comparable to the persistence time of self-propulsion. Excellent. Okay, but so now we're going to think, okay, but that was a picture of two particles, and as, what's your name? Simon already alluded to, there is an effect that happens at higher densities, which is that at higher densities, more collisions are possible, right? So that should enhance this effect, right? Because I have more opportunities for this type of attractive interaction at higher densities, right? So let's think what happens at higher densities. So one effect, okay, is that I have more opportunities for collision. And some of them will be oriented in the correct way to make those collisions last a much longer time than we would expect for Brownian particles. Okay, so that means density should enhance this effect. Okay, then there's a different, oh yeah?
So they're going to form clusters. So is there a threshold for the size of the clusters?
That's a great question. Can I come back to it? It's a really good question, but if I haven't answered it by the time we're done with motility and juiced phase separation, ask me again. Okay, sorry, I know it's a little low. I'll move over to this board. Okay, so higher densities give you more opportunities for collisions. Is there any competing effect that, as a function of density, would reduce sort of this type of effect? Yes, so there's a sort of feature that if I'm sort of surrounded by my neighbors and I'm bouncing around in a cage of my neighbors, then the time scale on which I change my actual velocity is not due to that rotational part, right? So let's bring terrible board work, Lisa. Okay. This, right? So if I was sort of at intermediate densities, then I would think that my velocity would mostly look like this. It would behave like the persistence time that I was sort of given in the first place. But if I'm at very high densities, because as your colleague already identified, that the actual velocity is changed by interactions, if I'm bouncing around in a cage of my neighbors, then my time to change my velocity is a lot faster, right? So it's like I basically had no persistence time again. Right? So another effect at high densities, and I'll write it down here and then I promise I'll move to the other board. So at higher densities, more opportunities for collisions, but also lots of collisions can reorient me. Like in a cage of my neighbors, can potentially reorient my velocity, and then I don't have this long persistence time anymore. So I'll just say, this just says reorient. Okay, good. Okay, so then, on completely sort of Gedunken thought grounds, we expect, okay, that if I have a higher Peclet number, okay, so if I have a higher velocity, remember Peclet number is the velocity divided by the rotational noise, essentially, right? So higher Peclet means a longer persistence length before I change my direction, right? Whereas a lower Peclet number means I'm more Brownian, okay? And so I expect that higher Peclet numbers should always enhance this effect, right? Because it's giving me more of this self-propulsion and less that looks like Brownian, and this is a purely non-equilibrium effect. Right? So I expect, based on purely thought grounds, that higher Peclet always equals more MIPS, more phase separation, right? Okay. But by purely thought, I expect that there should actually be sort of like a non-monotonic behavior in the density, right? So there should be like a sweet spot in the density, or equivalently the packing fraction, where this effect is enhanced. Right. And so if I get too high in my density, then I'm just rattling around in a cage of my neighbors, and that's where I get to that other, I start getting towards that other transition, which is the jamming-unjamming transition. And then I don't get motility. I still have a homogeneous state, but then it's a homogeneous, nearly jammed state. Okay? It's not phase separated. Okay? So what I expect is exactly what we drew over here. Okay? So that's exactly what we drew, because this is basically something, this axis is basically like a Peclet number for a fixed dr. Okay? But I'd really like to be able to explain in sort of some precision why there's a binodal and a spinodal and like what it's all about. Okay? And so I'm not going to go through all of the details, but what I did want to do, because I think it's a cute exercise, is to take that hydrodynamic theory that we developed last lecture and think about how we might adjust it for this system. Okay? So last time, you all have in your wonderfully handwritten notes, there's a hydrodynamic, sorry, I'm being an asshole now, hydrodynamic model that we had last time. Okay? But now we want to adjust it for a system that has no interactions between spins. Because we just have this steric interaction. Right? And we have, just to make sure that we're all on the same page here, each particle still has a polarization, but these polarizations don't interact with one another except through the steric interaction, right? That's what I mean by no alignment, okay? Cool. Now we can ask, in that case, what is left from our hydrodynamic theory? So we had a bazillion terms. Yeah?
So just a question about the jamming transition. Like, what would the jump state not moves?
What?
There's no freedom to move anymore when we're jumped.
Oh, you're asking.
Yeah.
Sorry. So it's a little subtle, actually, and I'm going to take a moment to answer.
I was wondering, like, because the potential is central, so I would expect to have conservation of momentum. So, like, how do we start from a system that has
Well,
particles going up in a
actually, I mean, can I just take a time out and say that's a great question, and one that, like, Phil Anderson pointed out about normal condensed matter? So let me all take a moment. Can you explain to me why any material becomes rigid? Okay, like, why are you able to stand on this floor? Okay? It's not a local effect. It's a completely emergent effect. And the way we explain it for crystalline systems is because of why the spontaneously broken symmetry. It's a rigidity is associated with that broken symmetry, right? Okay, but I also have glassy systems, like normal glasses, not even active glasses. And like, what the hell, man? Right? That is already, I think, a very deep question, is how do I think about what the broken symmetry is that's associated with normal matter? Okay, that gives it rigidity, because rigidity is a totally crazy thing. and actually that's what I spend a lot of my time thinking about in biological systems, and we might get to that, at the end. But, the other thing, in case that you want an answer, like if I had to answer that question for glasses right now, I would say there's really nice brand new evidence that it's a broken replica symmetry. So like there's all this work you may or may not know from statistical physics about replica symmetry breaking, and actually that seems to me to be the appropriate symmetry that's broken for those systems. Okay, cool. So hydrodynamic theories. Okay, what is left from our old hydrodynamic theory? Well, I shouldn't have, oh yeah? Right, so you're asking what is the density of the liquid phase, the high density phase. And actually let me think about it while I go to, because we are going to talk about that high and low density phase, and let me see if by the time we get there, I don't have a good answer right now.
Sorry if this is slightly non-secular, but I'm having trouble thinking about how to think about persistence length or the forward direction of the cells. Is that because of how they move through space that gives them a forward direction?
Oh, so you're asking, like, for a real biology system now, like, why does a real cell have a persistence length?
Yeah.
It's a great question. So it's highly cell type dependent, but there's maybe you've seen movies. There's probably the most visually appealing ones are keratocytes, which are these cell types that sort of look like a umbrella behind them, and they sort of go like this across things, okay? And so in that case, like for that particular example, it's because there is a system of actin network generated by ARP23 interacting with actin that basically polarizes, and it's generated by interactions with like the Golgi bodies and the centrosome. So like the cell gets set up to go this way, and then it stays this way for a long time with some orientational reorientations because it's got a structure inside of it that sort of has a memory. Does that help? And there's lots of other reasons that other cell types have persistence, but most of them have to do with sort of internal organization of cytoskeleton that takes some time to disassemble and move to a different point or to sort of move the assembly inside the cell. Great question. Okay, so what's left from our hydrodynamic theory? Okay, so I don't have sort of this ordered state anymore, right? Like because I don't have alignment of spins, I don't expect an ordered state. So I shouldn't have actually any of these terms that look like this. So we're not going to have ones that look like this anymore. We don't have an ordered state, so these things that look like grads of this sort of term squared. We won't have terms that look like this. Right, so we can get rid of all of those terms. In fact, the only ones we really have left in this sort of isotropic system where polarization really doesn't matter at all is we still have gradients in the density, of course, because that can still be there. And then we might expect I can have sort of coupling to first order between the density and the polarization vector because I'm just moving along, my polarization vector. And so we expect this. We expect this, and we expect all of these other terms to go away. Sort of, and I'm being hand wavy, but okay, that's the idea. Okay, so then if you sort of look, the only new ingredient that we need that we didn't have in our old hydrodynamic theory, we need one new ingredient. And it was one that one of your smart fellow students identified at the very beginning, which is that we don't have V0 anymore because as an important parameter because interactions can change my velocity, right? And so we should sort of not have that. Instead, we should have V of rho, which says that I might change my velocity depending on the local density. Okay, so that's it. And so then if you go back to your notes and look at that hydrodynamic equation and you say what's left, it's beautiful because almost nothing is. So we have dt of rho is still equal. So we still have the continuity equation exactly as before because that was really simple to begin with. And you notice I've replaced that V0 term now with just a V of rho. Okay, and then I have the equation for the polarization vector, but now it's incredibly simple because I got rid of all of those terrible terms. So I still have a term, and it turns out that it is the coefficient in front of p is just related to this rotational diffusion term. And then I have the term which looks like it's a gradient in rho. And it happens to have a v of rho in front of it. Okay, so these are the only terms I have left. Okay, yay. Yes? Oh, that is a great question. Can you give me 1 minute? And I'll get back to it. It's really good. Okay.
I've been using that answer a lot today.
I know, but I promise, like by the end, it will all, well, magically, no, it's probably untrue. But I really am about to talk about that in just a minute. And then I'm about to talk about clustering, like your question. I'll get there. Okay. All right. So the simplest assumption for V of rho, okay, is that it should depend on the density, and it should be, so it should, okay, show of hands. How many people think that the velocity should go up as the density increases? Excellent. How many people think it should go down? Yay! Okay, good. So we'll do the thing that people sort of do in physics. Oh, there's a question. That is a really good question. I have done something here which is evil, which is I have defined the polarization in a slightly different way so that it's not divided by rho in this set of equations. So, and the reason I've done that is to be consistent with the set of literature in the Cates-Taylor paper. So no, but only because I've defined it away. So it's a really good question. Yes. Sorry. But the literature is also terrible. So, okay. Okay. Good. And so what we're going to do is we're going to say V of rho. So one way of answering this question is to do a computer simulation and see what happens. And so like that's the first thing that one can do. And so if you do a computer simulation of these self-propelled particles, and at sort of various different Paclet numbers, you ask the question, how does this behave? You find that it very robustly behaves in the following way. So this is V of rho is a function of rho. What should V of rho be at 0 density? V naught. Great. Excellent. Okay, you're not asleep yet. Okay, and then as I go down, what people find very robustly is it's just a linear function for quite some time. Okay, and it sort of looks like it might, you know, the way that some people say it is they say, well, it kind of looks like a virial expansion, right? If you think about this as a state variable and you think this is the first order thing I should see, it's just, they write this is equal to V naught times 1 minus lambda rho, and this is the first virial coefficient. Okay, so I don't think that there is a really good reason to say this, except, well, maybe it's the first order thing that you might expect, but it is also, there seems to be a long range over which it's actually true in simulations too. So that's what we're going to use. Okay. Good, any other questions? Okay, so then you just put that in there. Oh, and the other thing we're going to do is we're going to take an adiabatic approximation, which is we're going to say, actually, at time scales where the time is much larger than 1 over dr, then this is sort of a fast equation, and I can set this side equal to 0, right? And so if I do that, so let me write that in words. So at time scales t is much greater than 1 over dr, I can solve this equation by setting the time derivative to 0. I could say it's in steady, it reaches steady state. And then I get that the polarization vector is just equal to 1 over negative 2 dr grad V of rho times rho. And then I can plug that in to equation 1. And then I get a very simple equation for the behavior of rho, which is that dt of rho is equal to plus the divergence of a nasty quantity, but not too nasty, V of rho quantity squared plus rho V of rho, and I'm going to call it V prime of rho just because I'm bad, but this is just the derivative of V with respect to rho. Okay, but it simplifies notation a little bit. Oh, of course I need a grad P over here still. That didn't go away. Grad rho. Good, and then this should be divided all by 2 dr. Okay, and the reason that I wrote it in this way is because I want you to notice that this looks like a generalized diffusion equation, much like you might get if you were looking for phase separation in a phase separating molecular fluid. So I'll call this quantity some big D of rho. And so you can think about this like a generalized diffusion constant. And when you do that, it's really nice because then, just as you do when you're doing sort of general phase separation problems, it's very simple. If this thing is positive, then you have normal diffusion, right? Okay, but if this thing is negative, that leads to an instability, right, and you get phase separation. So we want to know, when does that thing become negative? All right. Oh, did I? Sorry. Terrible board management.
You can push it up, and then I think we'll see. Yeah, push the button.
Oh, yeah. Good. Excellent. Up. This one down. And then you'll see it in a moment. Good. Thank you. All right. So when does D change sign? When does this capital D thingy change sign? Does it change sign even? Does it? Good question. Okay. So first of all, is V prime positive or negative? Is the derivative of this velocity I've defined with respect to rho positive or negative? Negative, right? So V prime is less than 0 always. Okay. So that means that this D does change sign, right? Okay, and when does it do that? Well, it does that when v of rho is less than negative rho of v prime of rho. Okay, and so since this goes down with increasing rho, right, and this goes up with increasing rho, and this is negative, of course, this means that it happens at higher densities, right? This thing becomes negative at a particular threshold. Okay, so at high rho. So as rho increases, this thing will go from positive to negative. Give me a thumbs up if this was cool. Give me a thumbs down if it's not cool. You got it? Okay, cool. Because this is sort of what we'll be talking about for a little while more. Okay, so to go further than this was, another example of hydrodynamic theory being somewhat useful. To go further than this, what you'd really want to do is it would be nice to have an expression for, because you want to actually calculate that binodal and the binodal and the spinodal line, right? And so to go further, what do you need? Well, really, you need a thermodynamic expression, right? So wouldn't it be nice to have expressions for thermodynamic quantities and in particular, the ones I'd like to have would be, for example, the pressure and the chemical potential, right? Because I can calculate the spinodal from when derivatives of the pressure become 0, and I can calculate the binodal from when the chemical potential of the dense phase and the not dense phase are equal, right? That's what I want. So I want P pressure, and I want, say, mu chemical potential. Okay, good. Okay, so now what do I do? So, well, there's some papers that have tried to do this, including some by us. So the paper that I would suggest reading first is this one by Takatori and Brady. And that's a PRE in 2015. And then we did some work too, a great graduate student, Jingbo Yang, with Christina Marchetti and I. So it's Yang, me, and Marchetti in 2014, and then a similar one, somewhat different, in PNAS in 2017. And between these three papers, you can get everything that I'm saying now plus a lot more. But those are the references for this. But what is it for? We're basically going to try to figure out how to calculate what a thermodynamic quantity like pressure should look like if there's a pressure analog in one of these active matter systems. Okay, and I'm not going to go into all of the details. I'm just going to say there are two contributions to the pressure. So let's say, okay, two contributions to pressure. Okay, and the first one's really cool because it's totally new. So one is an active, what Brady calls swim pressure. And I'm just going to say what it is because it's, I think, a little counterintuitive. It describes the flux of force, right? Because when you're talking about pressures, you're thinking about fluxes of forces, right? And it's the flux of force and let me call it it's the propulsive force, right? So these particles are self-propelled, which means they're carrying a propulsive force, right? So that means that there should be a pressure associated with it. And so the propulsive force, the flux, should look something like this, okay? Okay, and this is the flux that they're carrying, let's say, across a boundary. And this is just the force in the correct units and the direction that they're moving, okay? And I can write then, if I want to, a stress tensor actually, because it's not just a pressure, but it's a full stress tensor. And I can write it in the following way. Because once I have the force, then I just need to figure out what its flux across the boundary is. And it's this. And I'm not going to go through the details, but I think it's fairly straightforward once you accept that there is a force that it should be associated with the stress. Okay? there's a flux of force that should be associated with the stress. And then there's a more normal one, let me say, which is an interaction pressure, which is the one that people who have been simulating particle systems have been simulating forever, and I'll call it an interaction pressure. And it's just due to the forces that are generated by interactions between particles. Okay, and so that one's very straightforward. It's just, I'll write it in the following way, sigma on particle I, AB, and I'll call it an interaction potential. And that thing looks like the following. I'm going to write it down in 2D coordinates because maybe it would be helpful to some of you to see it. But it's basically a sum over neighbors of particle I of the forces times the sort of vector over which those forces are acting, so that you get something like flux. And then these are just some units to make sure you get the directionality right, because these are all unit vectors. But for the x and the y components, you get them correct. Okay, so all I'm saying is that if I have squishy particles that are smushed up against one another and they're interacting, then there should be a pressure, a stress tensor associated with those interactions, and this is what it is. Okay, and if you want to know more, I'm happy to talk after the lecture. Okay, so then what you can do if in a simulation is you can say, okay, the total pressure, right, is just total pressure should just be then, I'll call it P active. And I know it's terrible notation because like there's lots of P's running around, but okay. Should I call it pi? Would you like me to call it pi instead, or is that worse? Okay. I'll call it P active for active pressure. And it's just the trace over the sum of sigma interaction and sigma swim. So it's just what you think it should be. And if you do this in a simulation of one of these systems, so you can calculate these things, right, you find the following plots. So this is what P active looks like in a simulation as a function of rho for these systems that undergo motility-induced phase separation. At high Peclet numbers, it's just a monotonic curve. The pressure just increases with the density like you would expect. Okay, but as you get to higher Peclet numbers, so this was a low Peclet number, as you get to higher Peclet numbers, this happens. So you start to get a non-monotonic pressure with density curve, which of course is exactly what you would expect in a system that phase separates, right? Okay, and so you can say, okay, and so first of all, let me say what I'm drawing. This is the direction of higher Peclet number. As a reminder, the Peclet number I've defined here is V0 over 2R dr. Oh, I should warn you all. Brady defines the Peclet number in a totally weird way that's different from everyone else in the field. So just like, watch out. Peclet is weird. So it's sort of the opposite of what everyone else in the field, including Kate's and everyone else does. So just beware. Okay, good. But, you know, everything else is good. Okay. So, but this is the definition that we and everyone else use. Okay. So then, if I want to go back to this plot over here, the Spinola is really easy, right? I just can take the sort of derivative of the pressure with respect to the density, and when that's equal to 0, that should give me my Spinola line. So you take this, and you make a plot of when dp act divided by, well, the derivative with respect to rho, when that equals 0 is the Spinola, because that's when I become really unstable, right? And then you can say, okay, if I want to know the binodal, right, when that happens, then that happens in, that's where, right, that's the area where I get nucleation, right, where it's not immediately unstable. I have to overcome an energy barrier, but I can, right, because if I have a big enough fluctuation, I'll go downhill. And so to draw that line, I need a chemical potential. And so let me just write that. When the chemical potential is the same in the dense and dilute regions. Okay. And you can write, just using, again, assuming that this is a real pressure in thermodynamic, that this is just standard statistical physics. This is U active dn 1 minus rho times dp active dt. This is just an identity from statistical physics. And so basically, once you have this, you can do some thermodynamic integration of these simulations. And I'm not going to go into any of the details, but just from simulations, you can make a plot of mu active versus p active. And you can see that you get something that looks like this. So there's basically a phase coexistence point when the behavior of this curve as a function of the pressure totally changes. And again, if any of you have done work on phase separating, all of this phenomenology is a lot like what you get in phase separating mixtures. You don't really have to care about it too much or pay attention to the details unless you want to. The important thing is now you can figure out where this point is for every value of a Peclet number in a simulation. And then under this assumption that these are valid thermodynamic variables, you can predict where the binodal line is, and it matches up really well with the simulations themselves. So what does that mean, to take a step back, right? What we did is we sort of made up a definition for the pressure, right? You know, based on good arguments, but assuming that we could have a thermodynamic variable like pressure. And then we used it to derive both a binodal line and a spinodal line, and that seemed to work really well to explain the phase separation, right? And so that suggests, at least in this sense, this definition of pressure works. Now,
So you mean that row where you would expect the spinodal?
exactly, is exactly where it happens, you know, exactly, but within numerical error noise, whatever, it's where it happens. But I want to say that sort of, because you might think that this is a complete success and that this pressure is a really good thermodynamic variable, and it's not. And there's been a lot of papers recently, and I'm not going to talk about this today at all, but I'm happy to sort of talk to you about it if you care, that it doesn't behave the right way at all near boundaries. So like the pressure on a boundary generated by active matter systems is really funky and not given by what you might expect given these this sort of ansatz. And there's sort of open questions as to when and when not this actually works to describe what would be totally reasonable to define in terms of a pressure for an equilibrium system.
Can you motivate the relating the chemical potential to this pressure? What is that called?
I don't know. I honestly don't know. I should know, but I don't know. I mean, I think, so this is one of the, so I do know because I looked this up, like it is like one of the sort of things that you find in sort of, one of like Macquarie or something, but I didn't take the time to think of why, so I can't do it on the fly. Sorry. Okay. Yeah?
What is the small n?
Oh, that is the number count. So small n is just large n divided by v. Okay. Any other questions? Okay, cool. So the next thing that we want to do is to say maybe, actually, how much time do we have left? Like a half hour? Okay, everybody stand up, because this is the afternoon. Let's take a stretch break. Right? It's really been a long day. We're going to start something new. Now is a good time for a stretch. Take off my hot clothes. I know. Ooh. Oh, and I can tell my joke. I promised people a joke. Okay, I'm going to tell you the joke. Except it's highly disparaging to engineers. Is anybody, so like, no, I love engineers, okay, but it's highly disparaging. Okay, so, because it came up because like sheep jokes and stuff, okay, you know, okay. I had a picture of a sheep. It has nothing to do with herding or flocking sheep. Okay, so there were 3 people going to a conference in Scotland, okay? And one of them was an engineer, one of them was a physicist, and one of them was a mathematician, okay? And they're looking out at the beautiful countryside, and they see, you know, the pastoral nature, and they see sheep, okay? And in particular, they see a black sheep. And the engineer says, oh, that must mean that all sheep in Scotland are black, right? And the physicist laughs, ha ha ha, you silly engineer, that's not what it means. It just means that there's at least one sheep that is black in Scotland. And the mathematician looks at the two of them and shakes his head and says, no, you pathetic people, that's not what it means. It means there's at least one sheep that's at least half black in Scotland. All right, that's the joke. And okay, so I could tell you that the other funny thing about this joke is that my husband's the mathematician, and we disagree about who is being made fun of here, whether it's the mathematician and the physicist, right? So, because my husband's like, well, of course the mathematician is correct. Okay, everybody can sit down now. We're good. All right. So the topic we're going to talk about next is glass and jamming transitions. And really it's, would be a whole, in fact, there was a whole Boulder summer school on this 2 years ago. So obviously covering it in one lecture or half of one lecture is not possible. But I'm going to try to tell you some things that might be useful for people who are interested in these things. Okay. So at high densities, instead of having this behavior that V of rho sort of is equal to V0 times 1 minus lambda rho, this clearly breaks down at very high densities. And why is that? It's fairly obvious. It's because at very high densities, all of the particles are jammed together and they can't move anymore. Each particle is jammed by its neighbors, and so those interactions dominate over the self-propulsion. Okay. So, and the point that I want to make is that the system becomes solid-like. Okay, and what I really mean by that is that particles don't change neighbors. And that there's a shear modulus. We'll talk about that later. So they get stuck in a cage. Okay, what do I mean by that? How could you figure that out? Well, let's look at our old friend, the mean squared displacement. So t squared is a function of time. And I should really make this a delta t. So it's time window because we're assuming stationary state. And let's make this a log, make this a log, so it's a log-log plot. Right, and if I have a behavior that I'm looking at sort of on long times for self-propelled particles, we said on long enough times, those particles look diffusive, right? Because even though they sort of have a persistence length for some time, if I look at them for longer time, so looking at sort of long time behavior for systems, I'd get something that's slope 1 on a plot like this for diffusive behavior, maybe some different behavior at short times. Okay, but what you start to see in these systems that have glassy behavior is you start to see a plateau, and then eventually something that just levels off entirely. And so this is increasing density or packing fraction. And I'll just call it packing fraction because that's the relevant variable. And so, just as a reminder, this is, I know you saw it once already today, but maybe on a different board. This is, again, just the space that the particles take up. Okay. So, at high densities then, much of the physics should be able to be understood using techniques that we've developed a long time ago for solid state physics, right? That's the whole idea that we're going to be sort of thinking about. Okay, and so to get started on that, people have been trying to do this for a long time. Let me introduce something first, which is the jamming phase diagram. I'm going to draw it, and I'm going to talk about it a little bit. Okay. So on one axis, we have something which is fairly obvious, and I'll put it on this axis as 1 over the packing fraction. So as I go along this axis, as I go that way, I'm increasing the density, and so I should expect at some point, just if I take like a jar of, or actually even easier, some pennies on a table, right? If the pennies are spread out, I can move each penny individually, but if I smush all the pennies together tightly, then I can't, I have to move the whole penny pack, right? And so there's some density of pennies in my box at which I become rigid, okay? And so that's this axis here, and let's call the point at which I become rigid some special point phi j, okay? Then I can think, well, if I really want to deform my packing of pennies, right? So again, everyone's visualizing a packing of pennies on their desk, right? Then I could take them and I could shear them. right? And if I applied enough shear to them, they would start to change neighbors and move. So I could sort of unjam that penny system by applying a shear stress to it, right? They would change neighbors. Yeah? Oh, that they wouldn't pop out of plane? Yeah, exactly. So I'm assuming that we're just restricted to the in-plane system. Okay. So there should be some axis here that's applied shear or strain. And actually, an interesting question is whether the correct variable there is the shear stress or the strain. Okay, and then I could have another axis for a system in equilibrium, which would be the temperature, right? And so if instead of pennies, I had little colloidal particles and they were sitting in a bath, right? If I had them all tightly packed together, but then I started to inject energy by turning up the temperature, you could imagine at some point that jam system would start to melt, right? And so I can go also through a transition from a fluid to a solid by changing the temperature. And of course, if I gave you a glass of water and said, here, change this into a solid, the first thing you would do is stick it in a freezer, right? That's how you normally think about generating solids from fluids, right, is this temperature axis. Okay, and so if you sort of ask, when do I get a solid and when do I get a fluid or an unjammed system, you know, there's some question marks about like what happens in various limits, and so this is sort of a very rough approximation, and people have learned that this sits kind of here. Okay, but anyway, the important point is that this back corner of this diagram is a solid, and this area outside of this diagram, does everybody see this is like a three-dimensional diagram and there's like a back corner of it? Okay, and then this is sort of fluid-like or unjammed.
Okay, but if you're asking us to take something from a solid to a liquid,
Mm-hmm.
then we have to be bring the pressure, temperature, and volume, right? So inverse density is like volume.
Here I'm mixing together volume and pressure, right? And so, because really I'm allowed to sort of, if I have an equation of state, right, I can sort of say, okay, let me say fix one of those two variables and ask what happens on the third. So let's pretend I'm in a fixed volume system. Then that 1 over the phi is a pressure. Yeah.
So if you were to change another parameter like activity or adhesion, would that be the temperature axis? Or?
Oh, that's a great question. So let me come back. No, I won't have time to come back. I'm lying to you. Activity can be all of these things at once. Okay, so saying exactly how activity affects this is like a really interesting open question. Adhesion is easier. It's for sort of a pretty large class of like adhesive colloidal systems. You can basically divide the temperature axis by a sort of adhesive energy term, and that gets it about right. So if you have some adhesion, you can just divide the temperature by the adhesion axis here, and it gets it about right. Yes?
What's up with this sort of slice of pie where that goes to the shear axis?
That's really cool. That was something that's been sort of discovered in the last decade, which is that you can actually unjam a system by shearing it, or you can jam a system by shearing it. So I just told you the pennies, you could sort of unjam it by shearing it, right? But you can imagine actually that for some systems, depending on the way that you set it up, and actually that line says sort of generically, you can shear it for a little bit, and well, actually you can drive it to be jammed if it was unjammed. So if it's a little bit less than jammed and you sort of shear it a little bit, it can jam. That's what it means. And, you know, and again, I'd be actually, because this is a field that I work on for research, and so if anybody wants to come talk to me about any of what I'm saying, like in detail, I'm happy to chat you up. Okay, so that's the jamming phase diagram. Okay, and so let me say a few brief, sadly brief words about jamming, because it's a very cool topic, I think. Obviously, I work on it, so I'm biased. Okay. So I got asked a really good question about percolation and whether rigidity can be thought of percolation. I think one of the easiest ways to think about the jamming transition is by thinking about it sort of in mean field. It's sort of surprising you can. So it is, the jamming transition is a rigidity transition, okay, that occurs at 0 temperature, by which I mean there's no thermal fluctuations, in disordered packings of soft repulsive spheres. Okay, and it occurs at a critical packing fraction critical packing fraction phi j. And what you see, if you actually start to simulate these systems, is for phi less than phi j, all of the particles have no contacts because they can all move around so that they're not contacting anyone, and that's the lowest energy state. And then for phi equal to phi j, you find that the system is isostatic, perfectly isostatic. Let me say what this means. It's cute. Okay, so isostatic is the point at which the number of degrees of freedom in a system perfectly equal the number of constraints. So in a system of these particles, the number of degrees of freedom is easy. It's just the number of dimensions times the number of particles, right? Because each particle can move this way or that way. That's the degrees of freedom. And the number of constraints, that's equal to z over 2 times n. So now I got to tell you what z is. So z is just the number of contacts per particle, right? So this particle has a number of 3 contacts. And that I divide by 2 because each one of those contacts is shared by 2 particles. Yes?
How does the shape of the box affect the jamming condition?
So there's a short answer to that, which that's precisely what I mean by shear, because you can think about basically shearing is, one way of thinking about shearing is I'm changing the effective shape of an extra degree of freedom, which is the box. But we're going to actually, hopefully next lecture, I'm going to spend probably 20 minutes of the lecture talking about the shape of a box and deriving a shear modulus for these systems, just because I think in many cases in biology it's really useful to be able to, like in these emergent systems, because to figure out if your system is rigid or not, you need to know if it has a shear modulus, right? And so the shear modulus is just the second derivative of the energy with respect to the box degrees of freedom, right? And so we're going to talk about that for a long time next time. Yeah?
What about the area? So I'm imagining that you can tune your area so that irrespective of how many points you put in the box, there will always be some free area. It will always be flexible.
So I don't think that's, so the game that we're playing is you give me a distribution of particle sizes, fix that, and then...
Let's just say it's all particles are of the same size.
That's fine. But you could also just give me a distribution and a polydispersed distribution of them too. And my claim is that sort of there's often in these systems a crystalline minimum energy state, but it's a set of measure 0. And so given sort of any preparation protocol, you tend to find these disordered states which don't have any extra free volume to move around. That's the claim. Okay.
So can you give us an example of a biological jamming transition?
I can...
We'll get back to me.
So I would argue that most biological systems don't... so actually, it is, in my opinion, it's an open question if some groups of cells exhibit jamming transitions. Obvious candidates for it are bacteria that do not generate sort of polysaccharide biofilms. And there's some papers out there that suggest that this, actually there's a really nice paper by Oche Campas's group at UC Santa Barbara that claims, I think with fairly convincing evidence, that this type of jamming transition governs the rheology of the zebrafish tailbud. Cool, right? But tomorrow I will talk about a different type of models which have these topological interactions instead of metric interactions. And then my group and others have, I think, some very convincing data that a rigidity transition also happens in groups of cells of that type. But it's a different type of jamming transition than this one. So I think it's still open, although Oche Campas's paper, I think, is fairly suggestive that this type of jamming transition is really governing that process. So I saw this question first.
Is MET an example of this?
Oh, that's a great question. So the mesenchymal to epithelial transition or vice versa. It is, okay, so the short answer is no, because MET and EMT are actually a whole suite of changes to cell structure and shape and whether they generate proteases and stuff. Okay, so the way a biologist talks about EMT, it's definitely not a jamming-unjamming transition. But it could be that the set of changes that are associated with EMT, some of them may cause an unjamming transition or not. That's a good question. Yeah?
So a lot of cells are not spherical, they're mass-spike ratio.
Yes.
Does that just is changing the number of constraints that you have, or does anything else?
That's a great question. So it changes both your degrees of freedom and the constraints. And so there's a lovely set of papers that actually you can, okay, I probably don't have time to talk in detail about this, but that have looked very carefully at jamming of ellipsoids to get at that question. And it turns out that you get like different bands in the density of states. There's rotational degrees of freedom that become decoupled from the translational degrees of freedom. And it's really cool, and it totally all makes sense. So yes. But I would say next time, tomorrow, we're going to talk about systems where the cells are space-filling, and then you get into a whole different, I think, universality class, when they're not just shapes that have free volume around them, but instead they're space-filling. That's different. Cool. Okay, so just to finish this little piece, then you can see that when these two things exactly equal each other happens when ZC is equal to 2 times D. And so if you get to this critical point, so you can imagine it. I have like a bunch of pennies, and none of them are touching. And then at this critical point, each of them has on average 4 nearest neighbors. Right? Which is kind of like crazy, right? It's very mean fieldy. Like, how does it self-organize to do that is interesting. Okay. But it has, you can already...
D is the dimension of the system.
Yeah, D is the dimension of the system here. Thanks. Okay. And so then I just told you, you should expect this thing to be weird because it's very self-organized in a weird way to have this magical property. And it also has some very weird vibrational properties. And the reason I'm going to talk about the vibrational properties is because even though I definitely am not going to have time to get it to it today, it's very likely that some of the weirdnesses of these vibrational properties of amorphous solids are explain some of the weird features of active systems at that are sort of active solids. So maybe because I'm definitely not going to get there, I'll tell you a little bit about the phenomenology first, which is that if you look at normal glasses, okay, normal glasses have these things that are called dynamical heterogeneities. So this is like a picture of a colloidal glass. So these are like little spheres that are sort of thermally agitated, okay, but they're very dense, and so they form a glass, which means they don't change neighbors very often. And so these are displacements of now a simulated colloid, but you can see there's patches that are moving and patches that are incredibly still, and that there is sort of these patches can be very large, okay, that are moving, and so that phenomena is called dynamical heterogeneities. And one of the things in the glass field has been to try to understand that. I don't think I'll have time to talk about it too much, but I want to show you a picture now generated by a woman named Silke Henkes. And let me see if I can play this other movie too. So these are some simulations of self-propelled particles. It's just this model I wrote down, exactly the model I wrote down. And this is at a slightly, well, not slightly, a lower density. And this is at a higher density. And so it turns out actually that their self-propulsion speeds are the same. But what you can see, I think, is that the dynamics in this is really quite different from the dynamics of this. In fact, I think you can probably kind of tell already that what's happening here is you're exciting sort of low frequency sound modes of this solid. Okay, if you think about what the sound modes would be in this solid. And the question is sort of why? Because if this was a Brownian system, you just were agitating it thermally, you wouldn't sit on top of the sound modes of the system. You'd have equipartition, right? Okay? And so there's something really interesting about how persistent activity gives you basically the lowest frequency modes in the system only. Okay? And I can talk about that in depth more. But that's the reason why I want to talk to you about the vibrational properties of glasses, because it turns out that the dynamics of active matter depends very much on the low frequency properties of the solid. Okay? Cool. So in the last 15 minutes, 10 minutes, 10, okay? Let's talk about vibrational properties and stuff like this. And so there's some math, but not too much. Okay. So let's talk about linear response. Okay, so let's say I have a packing of particles and I apply a, let's say displacement, because I could either apply a force to each particle or I could apply a displacement on each particle, but let's say I displace all of the particles in this jammed packing a little bit, okay? So this little vector is, you know, the displacement I put on each particle, and I can write that as a column vector. So big U is equal to some displacement vector U1x, U on particle 1 in the y direction, you know, and so on, okay? And so this is just the sort of sum. I could put like a very small displacement on this one, and I could choose to put a very large displacement on this one, right? And so I fix this, I just impose it, right, which is a vector I put on every particle. And then I want to know the linear response, and so of course the question I'm going to ask is what's the vector of forces that result from me putting that displacement on the particles. So F1x, F1y, and so on for each particles. And this, of course, is nd by 1. This is also, I switched from big D to little d. Does it matter? Do people like big D or little d better? Big D. Okay. And so I'm looking at a field of forces. So right, each one of these displacements on the particles, because of its interaction with other things, there's a restoring force on it in some other direction. So let's say this is particle 1, so this would be F1, right? And those are its two components. And each one of these has a restoring force. Cool? So the definition of the dynamical matrix, which is just the linear response, so, and many of you may have seen it in a solid state physics class, is it's just the matrix that tells you the linear response of how I get these forces based on those that displacement field. Cool? Okay, great. So then I want to say, okay, how do I calculate that thing? And in systems that have a two-body interaction potential, it's especially simple. And again, if I would recommend Ashcroft and Merman if you want to know exactly why, because I'm going to write down an equation for what it is. But why it's precisely this, I think you actually need to go look up in Ashcroft and Merman, because there's some simplifications that you get that allow you to write down this very simple formula based on the symmetries of the dynamical matrix. And I'm not going to go through all that today. Instead, I'm just going to write the answer. Okay, so a dynamical matrix, it should have these indices, which look terrible, but I promise they're not. Okay, so for I not equal to j, so this is particle index 1, and this is a second particle index, right? So these i's and j's are particle indices, and these alphas and betas are dimension indices, right? So this makes sure that I have a matrix which is n times d by m times n times d, which is what I need to make that linear algebra correct, right? This is equal to the second derivative of the interparticle potential with respect to the particle positions. Okay. Okay, and the only thing that's a little magical about this is that the symmetries of the dynamical matrix allow these to be particle positions instead of particle displacements. Okay, because you would define it in terms of particle displacements, but it turns out you can write it in terms of particle positions, which is nice. Oh yeah, J beta. Thank you. And if I want to know the on-diagonal terms, the on-diagonal terms are just the sum of the off-diagonal terms. So I can write that as sum over j of d v rij divided by d ri alpha d rj beta. Okay, so this just ensures that basically I have force balance in a solid state. And I'm not going to go through the details. But I will note briefly that it looks a lot like the random graph Laplacian that you saw from Eleni yesterday. It's very close to a random graph Laplacian, actually. Okay, cool. So now, so now I have this matrix. I've defined it. Okay, so what should I do next if I'm a physicist? If I have, so what I do, okay, if I was having a crystalline solid, right, then the symmetries of the lattice would make this a much, much smaller matrix, right? Right now this thing is n times d by n times d, all right? And so what I would do if this was a crystal is I'd find the normal modes, and then I'd make plots, and I'd make, like, dispersion relations. It would all be gorgeous, right? Okay? So now we're going to do the same thing, except it's not gorgeous anymore. It's horrible, right? So we're going to take the eigenvectors and the eigenvalues of this matrix. We're going to calculate them just by diagonalizing it. And then we're going to plot a histogram of the density of vibrational states. So this matrix has eigenvectors, which I'll probably, let me call them lambda. Lambda is like a frequency squared, okay? And it has, so this is eigenvectors, eigenvalues, and then later we might talk about some eigenvectors. But this is just, the density of states, of course, is just a histogram of the eigenvalues of this linear response matrix. Okay, and it looks crazy. So if, let's first do it for a crystalline solid. So this is the crazy one I'm saving for glasses. Let's do it for non-crazy stuff. So do people remember what that is? Density of states for like a d-dimensional solid. It's okay. It's okay. It's just the Debye. So there's Debye theory, and you have a dispersion relation if you remember things that are like this that say that the frequency looks like some sound speed times some wave number. And then if you just integrate that for the Debye model, you get that the density of states in d dimensions is omega to the d minus 1. Okay? So in, say, 3D, where a lot of things live, then you get something like the density of states goes like omega squared. So if this is the log of the density of states, goes like this, and then some other stuff happens. There's Van Hove singularities, blah, blah, blah. Okay? What you see in this class of materials is you see something which is really weird. There's a very steep power law, but it appears to be universal. It goes as omega to the 4th, weirdly, at the lowest frequencies. Then there's this big flat plateau thingy, okay? And then this, finally there's some Debye cutoff, okay? Just like all materials. But this flat part here is called the boson peak, and it's universal. And it gives rise to weird heat capacities and stuff. And then there's this pretty small region, and so this little transition thing is often called omega star. But the reason I'm drawing all of this out for you is that these two regions have vastly different shapes of their modes. Okay, so if I look at the modes that are in the sort of very lowest frequencies for disordered solids, there's some mixture of things that look really highly localized like this, and that look like every once in a while there's a plane wave mixed in, because these things are solids, okay? There's something like a plane wave too. But neither of these, but plane waves are not good sort of like quantum numbers for disordered solids, so it's not really just a plane wave. Okay, in the boson peak, you get extended modes that are not really like a plane wave. They're pretty disordered, but they're kind of also very long and extended. And actually it turns out that this, like the boson peak and the extension of these modes is deeply related to isostaticity. The fact that you're right at the edge of this transition, and I'd be happy to explain why. But the important thing for us is that this is universal behavior, so we expect that any active matter system that inherits this universal behavior from glass physics has some of these localized excitations at low frequencies in it, and it also has some of these boson peak, like extended modes at low frequencies. And so I guess I have like 1 more minute. Do I have 1 more minute?
Yes, you have 1 more minute.
I have 1 more minute. I'm going to use it. Okay.
Go ahead.
Okay. Excellent. I'll use it erasing the board. No, okay. So the thing I want to show you is that all of this maybe for some of you is more easily understood by a picture of a potential energy landscape, right? So maybe some of you have seen potential energy landscapes, which has some energy of the whole system, maybe capital U, as a function of some reaction coordinate. And maybe you're familiar with the fact that in glasses, these potential energy landscapes are very rugged, look something like this. And the point that I want to make is these here are jammed, mechanically stable states, if this is a jammed packing. And the curvatures here, so I'm drawing it along one direction, but of course this is a potential energy landscape in n times d dimensional space. But these curvatures along, so if I replace reaction coordinate by like eigenvector 1 here, my lowest frequency eigenvector, then the curvature here would just be the eigenvalue, right? These eigenvalues describe the curvature of this potential energy landscape, okay? And so then the idea is that if I want to know how those active matter states transition from one configuration to the next very slowly, then I have to know how they jump these energy barriers, right? Okay. And the interesting thing is that in disordered systems, it seems to be the case that some of these localized excitations and some of these boson peak modes have very tiny energy barriers. So low curvatures are also associated with directions with low energy barriers. So putting it all together, and I'll talk about this a little bit more next time, what it means is if I have a system where activity allows me to sit on top of the very low frequency modes, it should mean that those low frequency modes might be a lot better at fluidizing the system, right, than equipartition modes, right? So what does that mean? That means maybe if I have systems at high activity, so high Peclet number, same amount of energy input, but just high Peclet number, this suggests that I should be able to fluidize the system just by changing the Peclet number and not the overall energy scale. In other words, I can have these types of excitations that I get to sit on top of because I happen to have this activity are especially good at allowing me to change between different metastable states. So that's kind of cool, right? Because it sort of suggests that this is active matter, like one of the differences between normal matter and active matter when it comes to Glassy and jam systems is the fact that the Peclet number, that the persistence, can actually help fluidize the system. Okay, that's the end of that.